I'm Ephraim, a graduate student at Washington University in St. Louis, working with Professor Henryk Ławczynski. And I'll be sharing a bit today about the design and then the data we took with our XL-Calibur balloon-borne hard X-ray polarimetry mission. We're looking at black holes and neutron stars. So before I fully start, just want to quickly throw up this list of our collaborators. They're all very instrumental to making this happen, spanning the US, Sweden, and Japan. Okay, so to start off with the big picture, why does XL-Calibur care about the polarization of hard X-rays? Well, to the already abundant timing, spectral, and spatial or imaging information that is already available from the current X-ray satellites, we wish to add polarization. And then polarization is especially useful when we're trying to learn about processes that have a preferred direction. For example, if a magnetic field is involved, or if we're looking at some extended structure around the black hole. And then polarization is also helpful for giving information when the objects that we're trying to see are too far away or too small for us to kind of spatially resolve, such as the surfaces on a neutron star. Up until now, the best results for hard X-ray polarimeters have been from POGO Plus, which flew about 10 years ago. They're also a balloon mission, and they're kind of a wider energy range. Our mission, XL-Calibur, is also in the hard X-rays. It's above IXPE, the Imaging X-ray Polarimetry Explorer, which is in below 10 keV. We're at 15 to 60 keV, and we're getting spectral polarimetry, so not just polarimetry compared to POGO. And then we also have a significant signal to background improvement over the previous iteration. Okay, now onto the design of the instrument itself. So on the left is a general schematic. On the right is one of the pictures after one of our launches that I took. If you were here for yesterday's sessions, there was mention of this one instrument that particularly abused how long it was possible to make the payload in the direction perpendicular to the direction to the launch vehicle, and that's us. We're very proud of the 12-meter-long truss. Right, and it needed to be that long because that's the focal length of the X-ray mirror. We've heard a little bit about that earlier. That focuses the photons down the length of the truss until they hit the detector setup at the other end. And then in the middle, we have the gondola, which houses WASP, the Wallops arcsecond pointer, which has been rightly praised many times already in the past few days. And their system is what allows us to point stably at these very precise, very small sources. Okay, now I'll describe each part in a bit more detail. First is another schematic of our amazing truss. Comes in three segments that we break apart for shipping across to Sweden. There's the mirror segment, gondola segment, detector segment, and then the honeycombs on either end support the mirror and the detector. And then here is a picture, I think I took this one, of XL-Calibur in the hangar in S-Range, Kiruna, Sweden, as we were integrating and testing and getting ready for launch, and provided for scale is one sitting PI. Next, the mirror that we use is a spare mirror from the Japanese Hitomi missions. The mirror had been already tested and checked for alignment multiple times with the detector setup prior to launch. This is kind of also what allows us to go from being a first-generation polarimeter without focusing optics to be able to get this higher signal to background ratio compared to POGO, which some of our collaborators had previously led. And then we also have a way to constantly check the overall alignment of the mirror, the truss, and the detector during flight. We have this LED ring that's mounted at the front of, but not blocking the aperture of the detector setup. And then there's this back-looking camera in the mirror that's constantly looking back and taking pictures of this LED ring, and then it's constantly comparing the LED ring position at any given moment to what we expect, and then it's usually just never more than a few millimeters off. And definitely, we've never used that to take pictures of anything else during testing. But what goes on when photons focused from the mirror actually hit the detector? So when they come in through the top of the detector, what we call the polarimeter, they first scatter inside the beryllium rod, low Z for good scattering. That's that teal color rod there, and then they are absorbed in one of the cadmium zinc telluride CZT detectors that are surrounding the beryllium rod. There are 4 boards, each with 4 CZT detectors, and each CZT detector is read out by 2 ASICs designed by the NRL. So all of this, the CZTs, the ASICs, the beryllium rod, all of this is housed within an anti-coincidence shield setup. The anti-coincidence shield is made up of BGO, bismuth, germanium oxide, scintillating crystal, and then it's 2 crystals. They're each read out by 4 PMTs, kind of covered by the black shades. The shield itself, it can provide this kind of background, passive background shielding, but also the active shielding comes when we get a hit in both the shield and the CCTs within a certain amount of microseconds. Then we know it's not coming from the direction that the mirror is focusing photons down, so we know that that's not the signal counts that we wish to look at, and we kind of veto those and don't look at those in our analysis. To elaborate a bit further on the detection principle, again, we have the mirror focusing photons into the polarimeter, into that detector setup. They're scattering in the beryllium rod into one of the 16 circumadjacent CCT detectors. But since photons that are polarized preferentially scatter in a direction that's perpendicular to their polarization, we'll kind of get a significant excess of photons in certain pixel positions compared to others. So on the bottom right, we have a plot of counts on the y-axis with the azimuthal angle around the beryllium rod on the x-axis. Additionally, when we know the results, the position of the pixel that each photon scatters into, we can also calculate what is known as the Stokes parameters, useful for polarimetry throughout different wavelengths. Stokes Q gives kind of the celestial north-south or east-west directions. Stokes U, the second column there, kind of gives the diagonal directions of polarization, and then we aren't able, X-ray polarimeters are not able to measure Stokes V, so we don't consider circular polarization. And then Stokes I is, of course, just the total number of counts to normalize Stokes Q and U. So we can combine Q, U, and I to form a polarization degree and polarization angle. I'll just call those PD and PA. PD is just the amount of polarization of the light that we're detecting. PA is the angle that the polarization vector points towards. And PD is P sub L here. I took this from the theory papers of one of our collaborators. Okay, on to the actual flight. We flew last year, early summer, 2024, July. Actually, it took longer than I thought. On the top left, we have a rough plot from CSBF of the general trajectory of XL-Calibur. I think the green is a bit hard to see, but it's bookended by the two schematics of XL-Calibur. So we launched in northern Sweden, went westwards until we had to terminate in, I think, Nunavut, Canada, for about 5 days, 5-day-long flight. And we split our flight between observations of the Crab Nebula and the black hole binary Cygnus X1. So for the Crab, we had about 50 kiloseconds of on-source time, and that corresponded to about 56,000 events, about 17 kiloseconds of off-source or background time. Then similarly for Cygnus, we had 69 kiloseconds of on-source time and 48 kiloseconds of background time. And then the MDP99s are about 8% for both. And what the MDP99 is, it means the minimum detectable polarization at 99% confidence. So it's like if we measure an amount of polarization, a PD, above that percentage, then we're 99% confident that it's not a fluke or that there actually was some polarization from the source. I'll talk a bit about the data from the Crab and then from Cygnus. For the Crab, we see a clear signal excess as expected in the spectrum on the top left. That's between 15 to 60 keV, which is our range of detection. This is a pre-response matrix spectrum. At the bottom, we have a light curve, so it counts as a function of time, on average, a 1.1 hertz on signal count rate, and then a constant about 0.3 hertz for the background, which is a much better, again, signal to background ratio compared to previous iterations of hard X-ray polarimeters. And then on the top right, we can see kind of an actual observed version of the modulation curve that I had shown earlier. We can also compare our results for the Crab measurements to previous PDs and PAs measured in the X-rays and gamma rays of the Crab Nebula. And then in red on the left, that's the XL-Calibur measurement of the polarization degree of the Crab Nebula and some of the best constraints in our energy range. And then on the right, we also have plotted the polarization angle of XL-Calibur, measured by XL-Calibur of the Crab compared to other measurements before, especially from IXPE in the orange, yellow, and green arrows, and then also OSO-8, the first X-ray polarimetry mission about 50 years ago or so. But we kind of clearly see a deviation in the polarization angle between the one measured by XL-Calibur and then the soft X-ray missions. So why might this be? Because as found by NuSTAR, which is a hard X-ray telescope, but without the polarimetry capabilities, the spatial extent size of the nebula seems to shrink as we get to higher energies. This is also kind of mirrored on the right when we see that the arrows that for the regions that IXPE observes, they get closer and closer to the spin axis of the pulsar, the star at the center of the nebula. when IXP is looking at smaller and smaller regions. So that kind of, taken together, they seem to indicate that the higher the energy, the smaller the size of the nebula that we're looking at, the more we're focusing in on that center portion. So again, this energy dependence, that kind of shows why it's important to look at X-ray polarization across the soft and hard X-ray bands to see kind of this evolution. And likewise, for Cygnus, we can compare the results between the soft X-rays, very precise XP magenta measurement, with our hard X-ray measurement in green. As you can see, it's a bit larger of an error than would be ideal, than we would like, but we were still able to see a significant overlap of the PA between the soft and the hard X-ray regimes, as well as an overlap between those two PAs with the radio jet from the system. So what could this alignment then with the radio jet mean? And I realize this is my fault. I didn't think to put this in when I made the slides, but if you can imagine for me kind of a black hole, there's this jet coming out the center. That's that yellow, white radio measurement there. And then we also have the accretion disk around the black hole, which is what you would see in interstellar. But out of all these, we know where these three components are, but we don't really know where the hot plasma, the corona around the black hole is. So what these X-ray polarization measurements allow us to say is to say that this is probably horizontally, this corona is probably horizontally or laterally extended, because when photons are emitted from that hot, bright thermal accretion disk, they, if they're scattering a lot in this laterally extended corona, they'll kind of have a polarization that's in the end aligned with the direction of the radio jet. So because of these X-ray polarization measurements, we're able to narrow down our conclusions of what the spatial extent and the location of the black hole corona is. Right. Right. So again, this plot on the left shows the polarization angle and polarization degree of Cygnus X1 in the soft, hard X-rays, and then as well as the gamma rays, soft gamma rays in the right. We clearly see a deviation in the PAs and PDs between the X-rays and the gamma rays, which hint toward some kind of probably difference in the emission process between these two energy regimes. In conclusion, XL-Calibur combines precision pointing, the spare X-ray mirror from Hitomi, as well as a well-shielded polarimeter to achieve some of the best results that we could for these sources on a suborbital flight. The paper for the crab has already been published, and for Cygnus should be coming out soon after review. And yeah, I think that's all. Thanks very much, and happy to try to answer any questions.